So my name is Mariusz Łapiński. I have this opportunity to show you something. The topic is a short tale about adding strings to each other. Actually, it is an effect of my work on the StringBuilder class for the C++. Some of you may know me. I see old faces. I see old faces of old friends from Evo Software, where I created probably one of my most sophisticated applications. It was called Ivona Control Center. It used a lot of different technologies all in one: MFC, WTL, ATL, boost signals to, well, leap curl, a lot of things. If you just Google it, you will find numerous ways to remove it and answers to questions like, is it a virus? Is it a Trojan? So later I worked at Intel, mainly on OpenGL driver for several years. Right now I'm working for EPAM systems in low latency computing. Basically, it's a huge system which processes orders sequentially. It has, first of all, it gives a sequence number to arriving order, so it has to process sequentially orders. Every node, every computer may go offline, may break, the RAM may fail, or anything, and so every node has to have its own backup. A lot of cool things, but let's start. I will start with telling you a joke. So there are 10 people in the world, those who know binary and those who don't, 10. I know it's not funny, yeah. I agree with you that this quote will serve as a purpose. So actually the characters of this joke will become handy. So let's build a table from these characters, right? There are 81 characters of this joke, right? We can encode them into ASCII characters, and it looks like this. So we need one additional byte to encode a null termination. Those are 7-bit encoding. How can we store a string in C++, right? We can do something like this, right? Let's play a game. What type is joke, right? So this is an array of characters, right? The first one will be produced by Visual Studio, the latter one by GCC and Clang. So it's an array of characters. You can modify them. We can do something like this. Those array can be const or const exp. The situation is pretty similar. Can we do something like this? That is store. Well, we can compile it somehow, but it will produce a warning for some reason, but it's basically deprecated. We shouldn't do it. And the options with const char pointer, the string literal naturally decays into const char and const exp const char, right? How about, yeah, and the type. How about this one? Well, it will be a pointer. Const literal easily decays into const char. We can write it explicitly, like this one. Even this one. Even this one. even this one. Well, we can, but you know, those free forms, better not to use them, because the compiler just don't pay attention to what you put in here and compile without any warnings. On all three compilers I present here, that is Visual Studio 2017, GCC 7.1 and CLang 4.0.1. So not the newest one, but you know. How about this one? We have auto ref. So we catch the string by a reference to a const array of characters. Explicitly, we can write this one, right? So 82, including no termination. Okay, other possibilities. Well, let's explicitly state that string is an array of characters. Okay, it's good, it will work, but you know, we do not want to explicitly state the length of the string. However, we can do it const exp, and it will finally work. We can use two array, okay, and with const exp, so it looks like an ideal solution, right? But when I was trying this, only GCC 7.1 was able to compile it in this form. We can try the string view without the second parameter, which is the length. And I was only compile it with CLang 4.0.1. So sorry, that version. I was only compiled with CLang const exp. String view, given this parameter, first what it does, it calls the chart rate's length to measure its length. It's not a const exp member function, static member function, but the CLang is able to do it at compile time. But we can always specify the length if we must. And the last option, commonly known std string. Okay, let's analyze this case. We have a string. We can sum it with a string literal. We can append something. We can append and specify how many characters will it be. Or we can use plus equals operator, which is basically the same as append in the middle. Well, let's take a look at libc++ using the GCC implementation of the std string. Initially, it is empty. It contains no characters. We see just garbage, right? 32 bytes of garbage. But if we add something, we see it's some of those fields are not garbage, like the length. It is on the second keyword, right? We still do not know what are the other things. Like here on the red, we see characters, including null termination. We add. So sorry. This is the pointer. The pointer pointing to the characters in place, directly in this object. So if we add some additional characters, we see those populate the last two keywords of the string, and the length increases as well. If we add some more, we cannot store everything in place. So we have the third keyword becomes the capacity, and the pointer points to heap allocated space. If we add some more, we see that the capacity of the next allocated chunk increases in some manner like multiplied by 2. The benefit of this approach is that we always have a pointer, always, which points to some data, always have the size, the capacity appears only if this is not small string optimization. Regarding the Visual Studio, it's somehow similar, but the differences are the in-place strings. In the beginning, we have always have length and capacity, right? If we add more than 15 characters, the first keyword will become a pointer. So 2 different approaches. If you take a FB string, they have 24 bytes of SSO. For instance, this is just one of the approaches. Okay, let's proceed with some real benchmark. Let's try to build a word, our joke, from separate words, right? And then let's do it first in Java. Yeah. So we have an array string, concatenate them. First, this time means we measure the mean value. Actually, it's a mean of averages to have some more stability of times. Initially, Java provides some worse results, but after some time, when the JVM gets warmer and warmer, it creates more optimal version. We can use string join. These are nanoseconds. This is Skylake i5-650U, something like this processor. I mean, we can plus equals strings, and basically it's the same as this, summing it, because in Java strings are immutable. So every time we create something, we have to spawn a new object. Java, like C#, provides other threads for garbage collection. So a lot of things happens here we do not see. Here we have the StringBuilder class, which is dedicated for the purpose of merging strings into a single one. Because the strings are immutable, StringBuilder is supplied. And we see the time is better, 400 nanoseconds. We can pass the size, expected size, initially like this, and the time is even better. What can we do? We can even reuse the StringBuilder object, reuse it, right? Allocate it here, delete the content with each loop, and we have 300 nanoseconds. Let's remember that number, 300 nanoseconds. Okay, how about C#? We can do this in the optimal way. Plus word gives 1 microsecond, plus equals gives the same because strings are immutable. We can use the StringBuilder. The time is even better. We can reserve the space initially. The time is even better. We can reuse the object. And the time is also 300 nanoseconds. Let's remember this number. How about C++? Right, we have an array of words, 33 words. We are merging. First we start with string stream. Right, we iterate over the words and just append them one after another. Let's call this a loop. A loop as a model of appending. We have a loop over the words. And the time is interesting, right? 2 microseconds over 2.5 in Visual Studio. Newest Visual Studio and GCC 1 microsecond. Okay. a friend of mine told me, okay, why not use str stream? Actually, str stream, which is, I think it is deprecated, performs similarly. So let.
Have you tried passing an array of the string?
Yeah.
And how does it help?
I will show you. Well, here you have literals which can be passed as an array of characters, right? So let's call this model flat. And here are the times. Pretty similar. Strange. I thought it will be faster than in C# and Java. Well, it's not. Operator left less just receive const_char pointer, calls char traits length. There is no special overload for array of characters. The time is slightly better, so but still it can be better. Let's try something different, adding static to the string stream and clearing it. That is doing the same as in Java and C# in previous slides, reusing the string stream object. So we added the content in loop or flat models. And those time are partially better, especially in GCC and C-Lang. Visual Studio did not get it. Yeah, I did not want it to be, comparison of different compilers. But if we manage to go through all the slides, it will be clear none of this compiler is better than the others. In some cases, the C-Lang knows it all. In some cases, Visual Studio is better. In some cases, GCC. So let's see. How about thread local, right? Can we do it? Similarly. Okay, let's try different approach. Let's leave string stream and try string, like this one. We see what happens here. We create an R value string, add it to string literal. The effect is some temporary string, add it. And the times are much more better. Visual Studio creates the first object first and calls the sign, then calls the sequence of appends, passing the pointers, interleaved with additional data copies, probably some data string moves. So we can do it better, like this one, when we have a single object and call append on it. And the times are slightly faster. Still, we are above 300 nanoseconds. Now Visual Studio does it quite well. Okay, how about the trick with the reserve, right? Okay, it works fine. The times are getting better and better. But let's switch back to the loop model for a while. First, it is without reserve or static or anything. The times are awful. Let's try text append. It's much better. Let's add reserve. Even better. And we see GCC at this moment is somehow faster than C# and Java. Well, it's questionable whether we can do such comparison because JVM and C# runtime, .NET runtime are, entire ecosystems with additional threads, but it's, I just wanted to show you the same similarly looking code in all three languages. Okay, how about static string with reserve? Pretty similar times. Maybe slightly better in some cases, maybe not in this one. But you have to be aware that those numbers, well, I did not lie in those numbers. I printed it what I get. However, they may be simply not accurate, especially when we allocate memory. So if you see 230 here and 285 here, it's possibly not so important. It's slower, but in some different context, it may behave better. Okay, thread local string, clearing, reserving, adding, similar times. Yet here for this flat model that is appending string literals, the time is pretty promising. Clang for some reason did not get it as good as the other compilers. Okay, let's disassemble this code into parts and start with something simple like measuring the length of the string. So const std char trace chars length, it's basically the same as str len. It costs nothing. Yeah, because all the compilers just know it, what happens here, and at runtime nothing happens. Okay, let's somehow bypass this issue and try to cheat on the optimizer. So the string has to be generated dynamically. Not in that form I presented to you. You have to dynamically allocate space, put some characters to be absolutely sure the optimizer will have no idea what is under this pointer. Take a look. 7 nanoseconds. Visual Studio, slightly worse results. Actually, this is the code for the length generated by Visual Studio. We see a simple loop, nothing happens, increment by 1 byte, and it loops looking for null termination. So it's hard to think how those compilers could generate something even faster than few lines of assembly code. Well, the answer is non-trivial. This is how ctrl-len looks in GCC. We have the PLT entry, which is procedural linkage table, which is patched during execution by the dynamic linker. So if you call ctrl-len, you will receive the best possible implementation on your platform. And this is only the fragment of the ctrl-len code. So I'm not sure what is happening here. Actually, the last time I was programming in assembler was in late 90s, I guess. So, but I see those registers, the 128-bit registers, so 16 bytes, 2 keywords, right? Those instructions are here to make a masks. So at once we can find where are the bytes with zeros, looking at 16 characters at once. So it is better than just looping 1 byte. Okay, how about this one? Nothing happens here. 1 nanosecond. But if you just somehow trigger optimizer to leave this instruction. You just clear the space for the std string. Okay, and this one we have 4 cases. 2 when we create strings from const literals, and 2 when we create from dynamically created joke earlier. And now for the first case, when we have string literal, those times are for CLang and GCC are strictly the times needed to allocate and deallocate the memory practically. Visual Studio does something more. In the second case, pretty similar. Dynamically built string actually enforces on GCC and CLang to pre-compute the length, so the times are slightly bigger. And the last case, the value drops. Okay, now we know how it. We have a glimpse of idea what are the times for constructing strings, for appending words, and different implementations. Let's start with simple implementation of in-place string builder. That is a class which serves a purpose of building a string by creating an instance of it and appending separate words of fragments of sentences in place, so it does not allocate any memory. Everything will store in place or in situ. It looks like this. We have a template size t in place size, a data, actually it should be std array. We have a std array of characters and the indication how many bytes we already appended. We append a word using operator left, which calls the length, calls the copy, and increment the consumed. str builds a new instance of std string on the data it contains. Looks simple. Let's measure times. As a reminder, it's a loop. Well, not bad. It could be better, right? Visual Studio owns it this time. Basically, it does exactly what the code explicitly states. No magic here. How about the flat model with string literals? The times are slightly better. But for CLang, he knows it all, right? Visual and GCC does the trick. They build the string sequentially by moving few letters at a time to the registers from the memory. So 1, 2, or 4 letters at a time. They load them from memory and store them into a buffer. Every time consumed is incremented. This reflects this series of append calls. CLang does something different. Actually, it copies the data, but the copy is just one instruction, and it does not load letters from memory. They are just hard-coded as immediate values directly into the assembly in the assembly code. So in case of CLang, it was just a very compact series of moves, which set the destination buffer to its values.
Basically optimize the memory reads.
Yeah. This does not read from memory. Not at all. Okay, what can we do here? Let's switch back to the operator left, which is our append for const char pointer. right? We have a length, which reads the str, the string, and we have a copy, which reads the str and writes to data plus consumed. Let's try a trick and prefetch those writes on data consumed before this length, because you can do it. Those are two separate steps. We can prefetch the destination data before the length itself. It looks like this. It's just as simple. This hint, this is Visual Studio. Yeah, it tells to populate all the cache levels, including L1. Let's see. The times are very, very similar. And in case of highly optimized code of CLang, the time only incremented. So we tried somehow to outsmart the compiler. It worked for some cases, but corrupted one case. Okay, how about this model? You know, let's not call the length a priori, but rather loop over the str and copy one byte after byte, byte after byte after byte. Let's see. This looks very promising. Those times are real good, right? It works, but only for our case, for our joke. Because when I try to benchmark, actually, when it's faster and in one context, in one context it is faster than calling the length beforehand, then I found out that this progressive approach, at least on this machine, works up to 6 characters. On stronger machines, even 4 characters. So it is not an option, at least if you want to just append few character words, but it's not the right solution. Okay, how about this one? Let's receive a reference to an array of characters. Let's assume that the last character is 0, right? How do you think? Pretty good. However, we can only apply this to the flat model when we use the string literals. But it works. However, we have to be, we are not sure whether the last character will be 0, right? Because someone may just pass an array of characters and the last one may be 7, for instance. It is possible, but in this particular case, we do not think about it. Exactly. But if it's not 0, then probably someone would think it wants this character as well. But it's a minor issue. It's rather irrelevant for the purpose of this presentation. Okay, so let's write in-place StringBuilder, which has 2 operators left. One for const-char pointer, and the second one for ref arrays. The problem is if we use this form, the second one will never be called. The string literals will decay easily into this non-templated overload, rather to overloads generated by this template member function. So to bypass this issue, actually, you need to make the first member function templated as well, and then it will work. Okay, let's sum up. Let's bring all the implementations all together, right? We have in-place StringBuilder, we have a progressive, CSTR, CRI, we have function to build a string, right? And we have array of characters and consumed, right? So those are the best times we are able to achieve. Right, the progressive model is appealing, but only in this case. But numbers are numbers, so I stated it in that form. In flat model, we see the times are pretty good. Can we do something more here? Well, it is possible, yeah. Uh, Actually, my implementation on GitHub have the make string function, which tries to determine whether other arguments can be stringified at compile time, and if so, it returns const string. So yeah, especially that sometimes compiler, if you put a in-place string builder on a stack and add some words, then everything may be compile time generated, despite the fact you cannot directly, write const exp to those methods and use it procedurally. I was thinking about this. We do not need std string. We can have string view and take a look what happens here. And those are the numbers we want to compare with C#, with Java. It was my very intent to show you that similar looking code in Java, C# and C++ does not automatically lead to conclusion that, oh, I write in C++, it must be faster. You have to put some work to make it faster. But it is surely possible, especially for those cases when nothing happens. Okay, in-place string builder has limited capacity, which is not always the case. Sometimes you simply do not want to create, 4K arrays on your stack or bigger. You have to use heap and dynamic allocations. Let's try different models. The first model, take a look here. We have a unique pointer of arrays of characters, right? We have something which designates the tail, initially pointing to the beginning of data, and some numbers saying how much space we have. Operator left. It's not so important. What is important, this model here, right? We have a data, we have a tail, we have a space left. Those are the times. Yeah, they look okay. Let's change it. So we have 2 pointers, right? To eliminate the size t, which is unsigned 64-bit integer. Let's use 2 pointers and just, it's a mistake here, obvious mistake. And we compare. No, it's not mistake, but I guess it won't compile without casting to diff pointer t. Yeah, but nevertheless, let's take a look at times. Similar, very similar. Okay, let's try something different. We have data, we have 2 size t, consumed, reserved. Similar as well, possibly GCC was able to produce some more optimal code and get below 300 nanoseconds. Okay, how about this model? We have unique pointer, and the consumed and reserved are remotely allocated along with the data. Pretty similar times. And actually, we want to use this model where we have a chunk with those data, because we'll have multiple chunks. And I mean that the string builder must track the head chunk and the tail chunk. If you add something to the string builder, right, initially those 2 points to null. If you add something, the code looks, I have no chunk, I have to create a new one. It allocates a chunk, head becomes tail, becomes new chunk, right? It's good. If we consume the available space in this chunk, we'll allocate a new chunk. We have another chunk. The head chunk will always remain the same and point to the first chunk. The tail chunk will follow the last chunk. So if you want to append something, we'll use the tail chunk. We'll get the head chunk only if we want to gather all the characters or iterate them from the beginning. This is good, but we saw that in-place string builder somehow works slightly better than those numbers I presented to you. What if we put a chunk inside the string builder? Some chunk with a size determined of the, at compile time, like this one. And this is rather, I'd say, strictly superior solution to the previous one. We can say that the in-place size is 0 and it will work. We can say in-place size is 4 kilobytes or 16 kilobytes. It will work well. The head chunk is always here. The tail chunk follows those successive nodes in this rope structure. It's singly linked list or rope, as you wish. And this model is good. Let's test it, but on some more sophisticated example. Let's call it a book, where we have our beloved joke just multiplied by 25,000. This code will produce 2 million characters. Sorry, I have some. Yeah. This 0 means the head chunk will exist, but its reserve will be 0. So with the first append, a new chunk will be allocated. Okay, so let's try some implementation of StringBuilder, the simplest one, without all the member functions. We see operator left, which does what we know, length and copy. But destination is determined by the claim member function. Claim checks whether there is some space left. If there is, then it claims the data by moving the consumed and returning a pointer to the place where we can store characters. Good. As you see, Visual Studio works better in this case. What can we do here? Well, first of all, this if condition, if it's true, calls prepare space, which is not a trivial member function. But it happens not very often, only when we have to reallocate the space. In my implementation of StringBuilder, when I allocate a new chunk, I take the size of the previous chunk, multiply by 2, align to the cache line, and so basically the growth factor is by 2. So to append 2 million characters, we probably need something like, I don't know, 13, 15 allocations without reserve call at the beginning. So this occurs very rarely, and we may take advantage of it by instructing the optimizer that this will happen rather unlikely. Unlikely can be used in GCC, CLang. In Visual Studio, we are unable to specify such intent that something could be likely or unlikely. However, Visual Studio has profile-guided optimization, which works pretty fine. I remember from the times working at Intel when we tried profile-guided optimization of the entire OpenGL driver for a particular test stream, that is some recording of OpenGL calls. The performance gain was up to 10%, even 10%, I remember. Nevertheless, let's see. It helped for GCC and CLang. For Visual Studio at the times they did the same. Actually, for CLang, not as good as for GCC. As I said earlier, this function is not trivial. It's probably one screen of code. Let's try to forbid inlining of this prepared space. You can do it in both Visual Studio and GCC and CLang. The results are as follows. For this particular example, it helps, but it's not said that in some different test scenarios it will help. But I wanted to show you that it is possible to use this kind of manipulation to achieve better performance result. So as some kind of summary, let's assume we have a chart when the x-axis is complexity of your code, the number of instructions your procedure, your method, your function does, and on y you have iteration count. How many times, with what intensity it is executed. So if you fall in low complexity or low number of iterations, then you probably do not need to optimize your code. But if you have high number of iterations and high complexity, right, you see that you have to somehow find a way to optimize the code. So this ought to be a hyperbola, but it looks strange. Okay, if your case is here, right, if you have very complex code with, I don't know, one iteration or few iterations, then you have to find a way to optimize the code by the processing models, right? To do something more smartly, to design a solution which is capable of let's say reusing the data. Do not do additional data copies, or do something smart, or do something right using the right algorithm, right? But as your code is simpler and simpler, and the number of iterations is pretty high, and this harms you because your code is too slow. You have 1 million of iterations, but only a few instructions. Then you probably need to find a better hardware or try to influence the competencies of the compiler, and try to guide him and instruct him looking at the assembler code generated by him. So as a practically last slide, I will show you some general rules for writing performant code. Measure before optimize, accept some architectural decisions and algorithms. You know, if you're lazy, you still do not write bubble sort because, you know, it's not important. I will just do it my way. No. So no algorithm or some decisions made early. It's best to automate the benchmarking, because if the performance optimization is one-time action in your project, then the performance will degrade over months with every commit made to the repository. Use std string to maintain ownership, to express having the physical, that is allocation, memory resource, and string view to designate the content of the string, not paying attention to the ownership. Newer compilers means better optimizer. It's interesting because as I use right now, and for those samples I run the code using, let's say, Visual Studio 2017. Microsoft releases new updates every few weeks, and as I automatically installed those updates, I saw performance increase in those in some of those test samples. So it is always a good idea to have that update than not having it. Try not to outsmart the compiler, because you may break something, right? But if you absolutely must, then let's be sure then you measure it, because you can corrupt very optimized code like the example with Clang. Telling him to prefetch the data just destroyed everything. Keeping data on stack is usually faster. It's not said that bigger in-place size will automatically lead to better times. But basically reducing dynamic allocation, that case with thread local and reserve worked pretty well. And the last one, well, pay attention to what's happening on your computer when trying to measure times, because strange things may happen. So I will end. If you want to take a look at this, my implementation of StringBuilder, then please find it on GitHub. You may mail me or find me on Steam. So thank you very much for attention. Sorry, it's I used 7 minutes too much. Any questions?
Yes. What was the offset for all the compilers? The option sets.
What options, right?
Yes, what options? Because it's actually very crucial for the performance.
Mm-hmm.
And to be honest, I'm very surprised that you saw any difference between the Flutter project and the performance that you mentioned there.
Well, it was for Visual Studio. It was optimization for maximum performance, I guess. For GCC and Clang, it was -02.
Yeah, right. I mean, well, basically the optimization level was the most interesting. So this optimization level, I'm certain that actually the loop was unrolled by the compiler totally. There should be no performance difference. How did you measure that? Well, I actually checked the tree count. It is pretty obvious in this case because the tree count is statically known.
Yeah, but compilers do not always enroll statically known loops.
Well, they do enroll the loops that are not statically known. I mean,
Yeah, but if you enroll like loop that has like 1,000 of elements,
yeah,
there's
yeah, but
actually class, for
yes,
example,
yes,
you
yes,
have
yes.
this has
Yes, that's
checks
true for thousands of elements, but there was 33 elements and the loop is totally unrolled.
Yeah, but there was a difference, and for every test sample, I take a look into the.
But interest is how did you measure that you saw the difference? I mean, because you only saw some average numbers, and there are many things that
Yes,
go wrong, like for example, that you said, running hierarchies in the background.
exactly.
it's
But
probably more beneficial to actually measure the lowest numbers than
Yeah, but did you just create a program that was running the loop 33 times, and that's it? Or did you use
no,
like a benchmarking framework like Google Benchmark?
I did not use Google Benchmark. At the time I started this project, it did not compile in C++17. I created my own simple benchmarking procedure, which looks like this, that there is some warm-up loop. Then we perform n number of iterations as the outer loop. There is an inner loop which does some different number of iterations, and inner loop provides the average time. Outer loop provides a series of average times, and I sort this array and find the mean value of averages. The exception to that was few last slides where there was a book, the model called book. Big allocations causes great instabilities of times. So I spent countless of hours basically running those test samples to achieve some legit values. And then in the last slides, I used the best of averages.
Okay, did you check the standard deviation for the averages?
No.
So it's hard to tell how much of an error there is.
I have a guess as to why it's different despite loop unrolling, because in the loop you have information loss, as in this the statically known length of the string. If you have it flat, the compiler knows this string is 3 characters, this string is 8 characters, and so on and so forth. And if it's in an array where the data length is, I think it was 33 characters or whatever you set it to, then even if that gets unrolled, the compiler still doesn't know the lengths of the string bits.
Well, in this case, if everything is local, I'm quite sure that the constant will be individual.
That's a pretty long, I'm not an expert, but that's a pretty long propagation path.
Not really. I mean, it's in the same function. It's like 2 steps. That's getting inside the loop, which is unroll. I mean, well, probably this discussion is probably further.
No, it's a very good question, but the aim of this presentation is just show you how it works on this computer. I use the basic compiler options for release version for Visual Studio and release for CMake generated projects for GCC and Silong, and those values vary, and if I would run the benchmark right now, I would probably receive some yet different values. And however, I did not want it to lie you. I just show you the code and how it works.
As a counter argument, you could say that if the compiler was able to track all information correctly, you could just build the string at compile time, which is probably what's happening in those super short
Yes,
GCC
it was exactly the super short cases. I mean, well, the final check is just to see what it was compiled to, right?
So this is my performance benchmark. Integer sequence is a case when you append integer values. I have my own custom function for serialization of integer values into a string, and there is just a lot of numbers. So those values are shown for comparative reasons, because obviously on different computers they would be different, and as you say, some different variants should work exactly the same. So minor differences you should not pay attention to minor differences of times, because even a single test case looped provides different values. And if you use a large chunks of allocated memory on heap, those times differ greatly.
If I were to nitpick, I think you should choose like the lowest values, because you reduce, because in the lowest case you can assume that everything went right. Cache was hot, allocation, like your memory was not fragmented, you didn't have any interrupts, your thread didn't to get reloaded and things like that. So probably that would make results a bit more stable.
Or use a pool allocator to take out.
I mean,
the
and
non-deterministic-
most micro benchmarks do that. So you just don't take the average, but the lowest one, or the average, or a couple of lowest ones. But
Yeah, the benchmark functions looks like this. So I should probably use this boost CPU clock rather than high resolution clock.
Hey guys, it is, we are having 1 p.m., so it's probably lunchtime.
Choose
And we can
what kind
continue
of
this
center
topic, right?
library you choose on Cloud, because I believe if you run this on Linux, I believe you use also SDC++ rather than with C++.
Exactly.
So I just want to know what kind of center library you choose with Cloud.
Well, this is my Linux. This is a special kernel module for Windows. It is called Ubuntu Subsystem for Windows, and it works just great.
I believe that uses the GCC standard library.
Yeah. So I can have, Visual Studio, I have C-Lang, I have GCC, and I have separate Visual Studio with Linux extensions, which connects to the local host, and I can disassembly the code run on the same very machine. So it's really great, this composition of tools. Okay. So let's end and go eat something. Thank you.